So the specific curve to that creates a public key and creates a private key that moves it and once you do little math, it's going to create a one for three both.
Hey guys, get started. So this week, we started our demos last Thursday. So those will continue this Thursday for those of you that still haven't presented. So you need to do that. And then for those of you that have already done that, you'll have a lab, right? So so today is gonna be more of a lab day, given that Thursday we're just gonna be doing that. And then you can work on these problems on Thursday. Those of you that are presenting will have to work on this Saturday or so. Okay, so that's kind of the idea. So today we're going to go over some commands that I have in openssl. We're going to study some things related to certificates and also keys, public keys, etc. And then there is a lab document here. I do have some slides, so download it. That should be opening. There it is. Right, so these are some of the slides. I will also go over these. We've already started with digital signatures. Obviously, you know how to do them. Hopefully, you've been, but it's just a short set of slides. So I'll cover that. And then there's going to be a little lab here about the bright space. So we'll work on the virtual machine. Okay. Yeah, so this one, the Word doc. So we'll work on this one today as well. So basically performance, if you remember, we had talked about performance a little bit already. And we did some analysis. And so we'll go over this problem. And then we'll go over this one. This is basically the same thing, doing digital signatures, but instead of doing it in Python, we'll do it in openssl. So that's kind of the idea. And then, we'll go over this problem as well. All right, so that's kind of, as I said, you have a lab. We have a lab today, basically, sort of related to digital signatures in general. And then we're going to look at some commands of that I have, also additional commands of openssl, basically. All right, any question? Oh, before I forget, currently this week is week 11. So that means next week is week 12. We have our exam, right? Our written exam next Tuesday. I'm still thinking about the we have to do the practical, right? So make sure you're practicing that. Key scripts are the ones for the demo, which you should have good command of because you did a demo. And then the other one is the RSA one, right? For breaking RSA, and then maybe the toy ones, because sometimes you could do operations there, right? Remember those? That's the bulk of it. I don't usually do openssl in the practical, so it'll be those Python scripts. So like I said, you're doing the demo, so you should be an expert, right? And then you have the RSA one, how to crack RSA, and then the other one. Any questions about all that? So it's possible we'll have the practical exam a week from Thursday.
Is the written exam cumulative?
Yes, because these things are, we look at the primitives and then it builds up to more complex things. So yes, you should understand symmetric encryption. Obviously, it'll be more towards RSA, but there could be a question there from the beginning. Good question. So it's closed notes, just like every previous exam, 10 problems with a cheat sheet. So you can have a cheat sheet, whatever you want on it, an 8.5 by 11 page. Anything else? Nope. All right, great. So yeah, so let's start looking at some of these. I'll do the slides just to get that out of the way. And then after that, we can just start the virtual machine and kind of play with openssl a little bit more. All right, so you guys are seeing there. So this one, public key certificates. So next week, we're going to do a nice lab, I think, where you become a certificate authority. You're going to have a client server architecture. And so you're going to understand a lot of that. But, basically, why do, we have public key certificates. Why do we need certificates? Because, it was that question that somebody says, this is my public key, but how do you trust them? Right? So there's got to be someone that you trust. And this is key. And this is usually a company such as VeriSign and several others. You'll see how basically these companies are going to be in your browser in like a Mozilla Firefox. So this will be the example that we will do. We will go to the browser, Mozilla Firefox, and what should be there? Basically, that certificate authority's public key will be there. So that way, whenever they sign something with their private key, the browser can check with their corresponding public key, and boom, you have trust. Okay, and that's going to be controlled by both the browser and the certificate authority, which are trusted. Does that make sense, guys? So that's a key concept, and we will look at that lab. All right, so we're going to continue here. So here's a really nice graph of a public key certificate. So if you look, what is provided there? Bob's public key in essence, right? Should Bob's public key be public and should it be encrypted? No, it doesn't need to be encrypted, right? In fact, it should be available to everyone, right? So you can see in this example here, we have the public key. So we have Bob's ID information. We have Bob's public key. The CA information is going to be there like, okay, this was signed by VeriSign, something like that. This is one of the things that today with openssl we'll play with, those kind of commands. And so what happens is, as you guys should know by now with a digital signature, you take a hash of it, right? So you take a hash of that public key and everything in there. If anything in that public key changes, boom, the hash changes completely and, it doesn't check out, right? So this is the concept that you guys have good command of. So you can see that graph there. So it takes, you can't see my mouse, but you can take the public key, hash it, and then you have that hash. And then now you're going to encrypt hash code with the CA's private key. Does that make sense? To provide authentication. And then that little signed becomes the signed certificate. That's the magic of it. And then you just append it to the public key. So now whenever you get someone's public key, you can trust it. You go to Amazon, right? You go to Amazon, let's say, and Amazon says, hey, this is my public key, so that we can have an encrypted communication, right? And here is my signed certificate, by the way. So then what's going to happen is in your browser, you're going to take that whole thing in the middle, right? That whole thing in the middle, and the browser is going to do what? It's going to take the clear text part, and it's going to hash it because it's going to know in there what hashing algorithm to use. And then it's going to also do what? It's going to take the signed certificate and it's going to decrypt the signature with the CA's public key. Where is that CA's public key? In the browser. Whose public key is it? VeriSign, for instance, the certificate authority. And then you get the hash. And then what do? You check both hashes. If they're equal, check. You guys understand? And boom, that's the key to the whole internet. That's how you guys do it. At that point, right, you have Amazon's public key. And what do you do with that Amazon public key? You can generate a symmetric key, encrypt it, send it to Amazon, and you can start buying things securely. And that works for the whole internet. That's the whole essence of it. Okay, so like I said, the lab next week, not this week, because we're still doing the demos, will basically entail this, but using openssl. So this will be an openssl kind of a thing where we will create a client server architecture and you will become your own certificate authorities. And then you will self-sign your keys and so that you can do this process. Okay. So when your browser tries to open this, initially it won't work because it won't have the public key of the certificate authority that you just created. So in order for this to work, you will have to load your public key information into the browser, and I'll show you guys how to do that. And then once you've done that, you're done. All right, so that's the key concept. Any questions on digital signatures? Obviously, this will be on the exam. Okay, perfect. And there's other tricks that you can do with cryptography. In fact, you guys know that we can build blockchain and cryptocurrency and things like that using these constructs, right? So this is just playing with the idea. So this is like digital envelope, kind of another way of doing things. It protects a message without needing to first arrange for sender and receiver to have the same secret key. Instead, it's kind of like you just send it there. So equates to the same thing as a sealed envelope containing an unsigned letter. So here you can see that the idea is creation of a digital envelope. So you have a message, obviously. And what do you do with the message? To achieve confidentiality, you encrypt it with some kind of random symmetric key. Boom. And then what do? Take that symmetric random key and encrypt that with the receiver's public key. And then you send both, right? The encrypted message and the encrypted symmetric key. And that's a digital envelope. You see, it's just play on the techniques. The digital envelope, then it's the two parts. And then you're going to use the receiver's private key to decrypt the encrypted symmetric key. And then once you have the encrypted symmetric key, you can decrypt the message. It's kind of the same, but just a little clever way of sending both things at the same time. All right. Any questions on this one? That makes sense. All right. Yeah. So okay. So just kind of to summarize digital signatures, right? Digital signatures. Suppose Alice sends a contract agreement to Bob. To avoid legal troubles, we'd like this communication of contracts to have the property of non-repudiation, right? Like a legal term. Bob should be assured that Alice can't back out of the deal by claiming she never sent the contract. Likewise, we want the property of integrity. Alice should be assured that Bob can't modify the contract and claim that the modified version is what Alice sent him. Okay, so there's a nice technique, as you now know, called the digital signature that provides these guarantees, right? So I could play a trick on you guys where I have two exams. I mean, it's kind of part of knowing the class, right? And I say only one of these exams you should answer. If you answer the other one, you get a 0, right? Mm-hmm. So what do you do there? I would basically say only take the one that I sent and not something that was not verified by me, right? So I could do something like that, or it could be done with a specific contract, but at the end of the day, it's just to check that I sent it, right? So the principle here is non-repudiation. So Alice simply computes a hash of the contract agreement, encrypts the hash with her private key, and sends the result, which is the electronic signature, along with the contract to Bob. Anyone can take that contract, hash it, and compare the result with what you get when you decrypt the electronic signature with Alice's public key. If it matches, then the contract must be exactly the same as what Alice sent, because Alice must send it, because only Alice can encrypt something that decrypts properly with Alice's public key, right? And the contract can have been modified because the hash value would have changed. So integrity and non-repudiation. Any questions? This is just summarizing the ideas that we have looked at before. So asymmetric public key encryption is almost magical, right? So you create security out of insecurity. However, there's still one weakness in the system that's fundamental. You see on a website something like, hi, I'm Bob, and my public key is so-and-so, which you know is the E and the N. But how do you know that that public key really belongs to the guy you know as Bob, right? Or girl, Mary, Alice, right? Well, you can be assured that if you encrypt a message with this key, only the key's owner will be able to decrypt it. How can you be sure that that key's owner is really Bob? That's the fundamental thing that we're going to discuss. We're discussing now. So if you trust a website on which the public key is posted, you might be comfortable. But at the end of the day, you have to trust whoever is presenting this key as belonging to Bob. And that trust is a security weakness. That was like the final thing of this whole archetype, this whole infrastructure, right? You can see how we started with, things in the Enigma box, right? And then we got symmetric key encryption, and then in the 70s, asymmetric encryption, and it just scaled until we get to this final problem of trust. And finally, this is solved with a certificate authority. There's got to be something that you finally trust, like an entity. And like I said, so the classic example here is like Amazon will go to VeriSign, sit down, have a cup of coffee, pay, present their IDs and everything, and VeriSign, the certificate authority, will sign their key. And then now they make this available, and then it's in the browser also, and that's the security finally. Any questions on that? That's the end of it, basically, of our security. All right, so that's kind of the slides that I wanted to do today to kind of summarize. Now we're just going to go over to our virtual machine and start playing with this lab, as I said. So this lab will be due a week from, maybe 2 weeks from Thursday, because we do have a lot coming up, right? So we're going to finish your demos, exam next Tuesday, and the practical exam possibly on a week from Thursday, okay? All right, great. So yeah, so let's start going over. So the next thing I'll do today is just go over some commands. And I want to show you the openssl. Okay. So I'll start. So there's 3 problems here. I'll start probably with number 2, because it's like the easiest one. It's a warm up. And I usually, when I do this class, I like to do both like the Python part and openssl. And so we'll take a look at it. But at the end of the day, they relate, because the keys come in the same format and things like that. But let's go over some of the problems. So performance. So I've stated many times that performance must be looked at whenever you're doing cryptography, right? This is a key thing. And the classic example is, yeah, we could have a really secure algorithm, but if it's slow, then it would take you an hour to download a movie from Netflix or something like that, and nobody wants that, right? So there's got to be a balance between security and efficiency. So we're going to do a performance problem, comparison of RSA versus AES. This is kind of just a experimental. We've already done one. And there are some built-in commands like this one also, by the way, that we can use just to test quickly and see performance. So we'll do that a little later. The other 2 problems are this one, create a digital signature. So we'll do this one. All right, so I'm going to start my VM. Okay, so let's start the virtual machine. Okay. All right, so wait for the virtual machine to load. All right, here we go. So these. All right, so let's open the terminal. So I'm going to CD into desktop. Here. /L. We'll CD into ITS 350 all 2024. ITS 354. Oh, there's 3 L's. Yeah. Okay. Sorry about that. All right. -L. So this is digital signatures. I'm going to create a new folder for this one. Just going to call it digital signature openssl. So mainly this is openssl today. Okay, and we are at the point today, if you remember at the beginning of the semester, I said I actually cannot define SSL, right? Today. I can't. The beginning, because there's so many, for you to really understand how SSL works, we have to go over all the individual primitives on how to build it. But we are now at the end of that, and I can say we can define SSL, and everything I say you will understand clearly. Okay, so we are there also. All right, so I've created the folder. Now I'm going to CD into it. Okay, here. Okay, so we are on the folder. All right, so let's read the problem. Create a digital signature in this task. So I'm doing problem 2, right? We will use openssl to generate digital signatures. Please prepare a file, example.txt, of any size. Please also prepare an RSA public and private key pair. So obviously, do the following: sign the SHA-256 hash of example.txt. Save the output in example.SHA-256. Then verify the digital signature in example SHA-256. Now we're going to repeat the exercise, but we're going to slightly modify example.txt and verify the digital signature again, right? So basically the thing that we've been doing all semester is like changing one bit, so you can use gedit, or we can just change it in the file basically. But you know for a fact, you should understand now that just changing one bit or one letter will change everything and it won't verify. So, you know, that would affect integrity. Please describe how you did the above operations, what commands do you use, etc. Explain your observations. Please also explain why digital signatures are useful, right? So don't forget to do that in the problem. So that should be pretty much it. Okay. All right. So, and then problem 3, we'll discuss. It's I was reading it. It's an interesting. I must have written this last year. Pretty interesting. All right. So let's do clear here. All right, so create a file. So I'm going to go ahead and just nano, what was it? Example txt, right? So example dot, whoops, txt. So nano example dot txt. Okay, and then we're just going to write something on here. You know, this is week 11 of fall 2024, and next week is the second exam. Okay, we're pretty excited about it. All right, so I'm going to do Control X when I enter. All right, so I have my file there. And now we just want to use openssl, right? So we're going to use openssl. So we have to create our public and private key. So that should be very clear to you. Pay attention to these because I'm going to give you a problem that uses all of this, but just might be a little bit more complex for you, okay? So that will be problem 3. So let's go ahead and do openssl. Okay, so let's do openssl genRSA, which we've used genRSA a couple of times this semester. So I'll show you today how to do with a password. So openssl genRSA dash pass out. And then you can say pass colon. And let's just use a number for password 13579 dash out. And I'm going to generate private dot pem. And as you know, we specified 1024. If I do 1024 as the size of the key, is that secure or insecure? Borderline secure, very secure. What if that's a true or false question on the exam? What do you say?
I think it was borderline.
Borderline insecure, right? Or secure, yeah. So yeah, very good, very good. So yeah, this is kind of how you have to think about these things, right? Because you don't want people to break this. All right, so let's go ahead. All right, great. So that's great. So genRSA private key, 1024-bit long modulus, the true primes. E is 65537 and everything. So let's go ahead and cat this private dot pem. And then, like I said, today we've seen the data like this a lot. Today I will give you a few additional commands to look into this a little bit more. All right, just to kind of get a feel for it. All right, now let's go ahead and generate our public key. So I'm going to say openssl. So let's take a look actually in the folder ls-l. As you can see, all I have in there is the private.pem file. That's the file that you should keep private, obviously. And then we're going to create another key to share for the exercise, okay? So with your partner. So now I can go ahead and do clear here. Open SSL. RSA dash pass in pass 13579 dash hub out dash hub out dash in private dot pem dash out public dot pem. And that should be it. All right, writing the RSA key. Now, if I do ls-l, you can see that I have my corresponding private and public key. Does that make sense, guys? So we've seen several ways of generating these keys with PyCryptoDome or with openssl, and this is the key to everything, okay? All right, so now they correspond to each other, and now we're going to think about the exercise of generating the digital signature. So we're going to sign basically example.txt, and it will create the file for the signature. In this example, I don't need confidentiality of the message. We only need basically non-repudiation, integrity, and authentication, right? These are the pillars of information assurance that are being addressed with this technique, but not confidentiality. Because, why not? Because this message will be readable to anyone. We're going to send it in clear text. Okay, so let's go ahead and do that one. So we're going to sign. So this is the signature problem. So I'm going to go ahead and just sign it. So you sign by doing openssl. You specify the hashing algorithm. So the digest should be in this case. I think the problem asks for SHA-256. And then dash sign, basically. That should tell you. We're going to use the private key, private.pem space dash out. And then it's going to be example dot SHA-256. I'm going to move this one further down. SHA-256, and obviously the input is example. Oops. Example.txt. Okay. All right, there we go. So now I do ls-l, and there it is, example dot SHA-256. I'm gonna cat that example. Right, and you can see it's some kind of an encrypted file. Got it? All right, so now you would send this information, right? So what would you send? You would send the signature, obviously. That's going to be example SHA-256. So if I give you a problem where you have to work with a partner, you have to think of the files that you have to send, right? So you would send example SHA-256. And would you send a private.pem? No. Good. You would send the example txt? Sure, as long as confidentiality is not one of the requirements. And then obviously public. Everyone can have the public key, right? So that's the whole point. All right, so now go ahead and send it. And the next step would be to verify. So how do we verify? So assume you've downloaded the correct files. Now we're going to go ahead and verify. So the same thing is openssl, okay? And then we have to specify the hashing algorithm. So digest, usually the term dash SHA-256. There we are. And then we're going to say dash verify. Verify. And then we're going to do public.pem. And then dash signature example dot SHA-256 example dot txt. And very much like in the examples of Pi Crypto Dome, what would you expect to get here? True or false, verify okay, verify false, right? That should be the expected outcome. No surprise, it says verify okay. Any questions, guys? Does this make sense? All right, great. Now, the problem states that we should modify one bit, right? So the problem states slightly modify the example txt, okay? And we're going to check it again. So we're going to do that basically. So let's go back to the virtual machine. I'm going to do G edit. That's not it. What am I thinking about? G-hex, right? That's what it is, G-hex. Yeah. Okay, so G-hex, open example txt. Yeah, the familiar one. So now I'm going to go ahead and change one bit. So, okay, I changed one bit of it. Save this. Right? Okay, perfect. So let's dash L. Let's take a look at example. You can see I've changed one bit of it. So now we're going to repeat the same exercise. Basically, we're just verifying, right? So we would do openssl egst dash SHA-256 dash verify public.pem dash signature example dot SHA 256 and then example dot txt. So what should be the outcome this time? Should say false, right? And there it is, verification failure. And that's the same concept that we did in pipe crypto dom. Does this make sense, guys? And that's it. That's problem 2. Pretty easy, right? So that's a demo of doing this. All right. Then now we're going to explore some other. So are there any questions before I move on to something else? Okay, seems like this is pretty clear. So that's one thing about this class, right? Everything is kind of the same thing, just adding an additional layer. All right, so let's go back to the Word document. So we did problem 2 completely. Let's look at the submission instructions here. Just you need to submit a detailed lab report to describe what you have done and what you have observed. You also need to provide an explanation of the observations that are interesting or surprising and answer all the questions. All right, great. So now let's take a look at problem 3. So problem 3 is for you guys. So using any symmetric encryption approach, send a message to your partner and achieve confidentiality. This time you must exchange the symmetric key securely and correctly using RSA. So you really know how to do all that. Additionally, add a digital signature to authenticate the required keys. Okay, so notice that you need to do that. You will need to create a certificate of authority as a trusted party. Now you only need to do this like not an actual certificate authority, but just the concept of a certificate authority in this problem. Does that make sense? So in next week's lab, you will actually use Linux commands to create a certificate authority. What I mean here is just use the private key. So the thing you need to sign here is the keys. Do you see what I'm saying? So there's so I ask you the following question. Think about this. The hard part here is how many keys do you need to create for this one? How many keys? For you to complete, practically, to solve this problem, how many keys do you need to have?
Three.
Which ones?
You need for public here.
Mm-hmm.
Just one group.
You really okay, but so in one direction, you're only doing this. Yeah, you're doing this in one direction. So the problem says using a symmetric encryption approach, send a message to your partner and achieve confidentiality using symmetric encryption, right? So that gives you a hint. Then this time you must exchange the symmetric key securely and correctly using RSA. But additionally, add a digital signature to authenticate the required keys. You will need to create a certificate authority CA as a trusted party, and only as a concept, as I said, not using the proper Linux commands. Because all I want you to do is think about this problem, what I'm asking. So it's not quite right what you said. So you need this. So think about it again. The key to understanding this is how many keys do you need to create? Or think of the parties involved. Who are the parties? So let's say Bob and Alice. There's a message involved that you need to encrypt with symmetric encryption. Then you need to exchange the key securely, right, with RSA. But I'm also asking you to use a digital signature to authenticate the required keys. And for that, you need to create a certificate authority as a trusted party. So that's an additional party involved. Do you guys understand? So you create your public and private key, and then you need to create this concept of a certificate authority, and they also need to create a public and a private key. So in fact, it would be the public and private for the certificate authority and the public and private for you, and then the symmetric key. Do you guys see that? why that is? Because the thing is, you need to sign the public, right? So add an additional signature to authenticate the required keys I sent. So which are the required keys? The public key. Do you guys understand? So this is the problem that I want you to do this time around. Okay, so I guess I should have had my whiteboard for this one. So we're gonna draw it out. And these are like you guys probably understand these concepts really well, but I keep every time adding a layer to the onion, right? And that might be the issue, but I like to do this problem before we do the next lab next week, because in that one, you'll be distracted by the whole process of creating a certificate authority. This one, you're just pretending to be one. And you're just gonna, by the way, you can just use openssl for this, okay? So so we're gonna draw this out. So hopefully. All right, so let's try the whiteboard here. All right, so let's go ahead and think about this one. Okay, so we have the little whiteboard there. All right, so what am I asking you to do? So we have a certificate authority, right? So this is the new concept that I'm introducing. So what does the certificate authority provide? It was in the slide, right? Is that trust, that party, right? So here you guys have like a message. You have a plain text message, right? You have Bob and you have Alice. Okay, so you need to send this over the insecure internet, right? So the first thing you're going to do is you need the symmetric key. So you're going to use something like AES, right? And you have a key for AES, right? You guys know that. And then you're going to encrypt the message with this, right? And now you have the cipher, which you're going to send to Alice, right? So you know that part. But then how do you exchange the key? You already know how to do that as well, right? So Bob is sending. So Bob has a pub and a private, and Alice has a pub and a private, right? So the key, this AES key, right, needs to be exchanged securely. So how do you do that? So how do you encrypt the key? So the key is over here. Cipher key from Bob, correct? To Alice. So how does Bob send that encrypted? What does Bob use? Anyone will take a guess? So Bob needs to send a cipher key, the AES key, securely to Alice. Yes, sir. Yeah, exactly, right. Alice's public key. You know how to do this, right? So exactly. So you use Alice's public. So I'm going to write it like here, Alice pub. Perfect. So goes into encrypting this, and then Alice will use her private key. So what I'm discussing today, you'll know how to do all of that, but the new concept is the certificate authority. You're going to say that you guys trust this certificate authority, right? And so what does the certificate authority need to do? They need to provide the digital signature. And what do they sign? They sign Alice's public key. So then you need to create a new entity called CA, which will have a public and a private key. Does that make sense? And you will be assuming that it is a trusted party. So that means that Bob has the CA pub, right? So Bob has the CA pub, and Alice also has the CA pub. You guys see that? So they have it. And then now Bob needs to, so actually who here, so how does it work? So in this case, you have Alice pub, right? And Bob is going to use it, but Bob needs to do what? Needs to trust it. And how is Bob going to trust this? Bob does trust the CA. That's the key. So Bob trusts the CA. So that means the CA will do what? Will sign Alice's pub with their private key. Do you understand? So here you get the CA private, which will sign Alice's pub. So now this has a digital signature that is received by Bob. And then what does Bob do? Verifies. Verifies with what? With the CA pub. Yeah. With the CA pub. Do you guys understand? That's like pretty much everything right there. But as you can see, as I said before at the beginning of the semester, you do end up with a lot of keys, right? In these kinds of ideas. So now this is the final part of this. And this is the problem that you have to implement. So you'll have to create a certificate authority, which is trusted, public and private. You'll have to create a public and a private for Bob, a public and a private for Alice, and also the symmetric key. You'll encrypt the message with the symmetric key, then exchange the secret key securely with RSA. Obviously, you would use Alice's public key, but you want to be able to trust Alice's public key. And in order for you to trust Alice's public key, you have to get a signature from someone that you do trust. So the idea kind of here is that, you might be communicating with 1,000 people, not just Alice. So you can't trust all of them, but you do trust the CA. This is the one party that you do trust. And so as long as that CA has met with all those and has signed them, you can trust it because you trust the CA itself. Any questions, guys, on this one? So that's the problem you have to do. That's your homework. You have to show evidence, right, that you created the public key for Alice. Then the CA will take that file, sign it. So you need to verify it and all that. And then once that's done, you can use the public key to exchange the key. And then once the key is exchanged, you can use that to encrypt. Any questions on this one? All right, sounds like you guys get it. So that's really great. All right, so that's I leave that problem for you guys to implement. So you can do that for your homework assignment. All right, so I'm going to stop the whiteboard here. Share. All right, so we've discussed and I've shown you how to do problem 2. We did that one. I demoed it, and then I've assigned problem 3 for you to work on, okay? And then we'll come back to problem 3 or problem 1, sorry, in a little bit. But for now, let's just go over a few additional openssl commands, okay? So just to make things even more complicated, do that with a partner. Actually, that would be good for you to do that with a partner, okay? So work with a partner. So your question should be, who creates the certificate authority? Either one of the two partners, right, would create the certificate authority. Does that make sense? And this, as I said, this is only the first introduction. Next week, we will do an actual lab, a very nice lab. So I can show you what we will do is pretty much the same concept, but instead of kind of just creating a certificate authority, just, with a very basic one, you will be creating one through Linux. Okay, through Linux has some functionality. for doing that. So you can see that'll be our first lab that is like an applications lab. So it should be this one, I think, public key cryptography. I'm going to click on it. And this comes with a really nice tutorial, by the way. So it should be pretty good. So we will do this one. You can see becoming a certificate authority. All right, so try to master this concept in the simple way, and then we will repeat this one again next week. This requires creation of a whole bunch of files, creating a certificate. You'll be and the assumption here is that you, instead of just Bob and Alice, here we're going to be creating like a Amazon.com or something like that, a fake one, obviously. And we will be simulating a web server, basically, so that it is the client server architecture. Yeah, please.
I want to make sure I just got everything right. So instead of just using Alice's public key, for example, you would encrypt that with the certificate of authority's private key.
Yes.
And then you, instead of using her regular public key, you use that encrypted certificate authority.
Well, no, you still use Alice's public key.
So you do?
Yeah, you do.
Without the certificate authority.
So the certificate authority just provides trust.
Yes.
So the digital signature, at the end of the day, what does the digital signature give you? Okay or not okay? Remember, true or false. So you still basically do what you know how to do already. Take a symmetric key, encrypt your message, exchange that key with public and private key. But now I'm adding this third component that before you use that public key, it's almost like, okay, I just received the public key from Alice, right? But I need to check it with my certificate authority. So I'm going to run it through the whole digital signature thing. If it says okay, then I can proceed as I know how to do with public keys.
So it's almost like integrity. Almost.
It's the trust of the certificate authority. So it's a type of, it's trust. So it's like, how do you, in the slides, right? So the underlying principle is non-repudiation, integrity, authentication. So those are the three underlying principles. But kind of the question is here, it's what I kind of wrote, the man in the middle attack. All right, so asymmetric public key encryption is almost magical. You create a security out of insecurity. However, there is still one weakness in the system that's fundamental. You see on a website something like, hi, I'm Bob, and this is my public key. Or in the problem, hi, I'm Alice, and this is my public key, right? So you see that. But how do you know that public key really belongs to the guy, Bob, or girl, Alice? See, that's the key question. And how do we solve that, right? Through trusting a certificate authority. Did I answer your question?
I understand like the concept. It's just like for problem 3, for example, when we're actually implementing it, going from concept to code, I just want to go step by step.
So all that the certificate authority will give you is okay or not. And it's just so that you have this additional check that you actually check that public key with a certificate authority and you can trust it now because you trust that certificate authority. That's the key thing. I know it sounds maybe abstract or something, but this is important because if I go to Chase or Bank of America right now and they say, this is my public key, okay, great, but I'm about to do a money transaction that could wipe out my entire savings, right? So you want to be certain that whoever says Bank of America is actually Bank of America because you could have this thing called a man in the middle attack. So what happens there, it doesn't matter that you can go to a fake Bank of America. The key thing is when they give you that public key, you no longer depend on their website to check that key. That key comes back to your browser, a trusted environment. So you go from untrusted, the web, to trusted environment, your browser. So you receive that public key and you were about to do the encryption, but there's one final check. The browser has the public key of trusted CAs, like friends of yours that have checked things out. One of them is VeriSign. That VeriSign will not be added in there if Mozilla doesn't allow it in there, that kind of thing. So when you bring in that public key from Bank of America, let's say it's somebody faking Bank of America because they want to steal your credentials. So you grab that public key and you check it with your browser, and then your browser is going to say, okay, that will have a certificate, right? So that's the whole. You're not going to grab something that doesn't have a certificate.
It's like
so
the errors that say like the certificate can be trusted.
Yes, exactly. That's actually the lab. The lab that we're going to do is exactly that. So when you bring that public key, which is wrapped in a certificate, it's going to be wrapped in a VeriSign certificate or any other CA that you trust. So that's the final check. That it's almost like you have VeriSign right there, and just before you go to the bank, it's going to check that thing and it's going to say, yes, I signed it. Okay. Because you have the public key of VeriSign. And they signed it somewhere else, like in a physical place with their private key, and you have their public key here. Once that okay happens, boom, you can start the whole process and communicate with that bank. But if it's a spoofed bank, obviously VeriSign did not sign that one. Do you see that? So the moment it comes in here, the VeriSign will check it and it'll say, no, I didn't sign it. Or if it's some other entity that you don't have in your browser, it's going to say, I just don't know this. Do you wish to trust this or something like that? So to answer your question, and actually that should be in the lab that I was discussing here. Okay, it may not be there, but you guys have experienced this. You go to a website and it says something strange like, I don't know this. Would you like to create an exception? Do you guys know what I'm talking about? And sometimes you click on that and you add an exception. Or sometimes you just go away, right? You're like, I don't trust this. Well, that's what's happening in the background. It didn't recognize that certificate of that key, and that's why it gave you that. But if you do everything properly, following this lab, it's not going to give you that, and instead it's just going to check it and let you go through the website. So that's the whole idea, right? Did I answer your question? Yeah. Did you have a question?
Yeah. Right.
Yeah.
Never like changing out. That's like what we did when we had a patch of it.
Mm-hmm.
That's all it is. Not like encrypting it at all.
It's not really, yeah, it's not encrypting it. That's right. Because the public is a good question, right? So the public key is public. There's nothing to encrypt. It's not changing it. And I think that this was also your question, like, why are we doing this? It's just a final check because what if this came from somewhere else? But it is the public key. That's public and it's just signed by somebody that you trust, such as VeriSign. Exactly that. And it does the hash because, yeah, exactly like the diagram that I had here also. So that was also in the slides here. Literally. Yeah, literally that. So that's Alice's, in this case, for our problem public, which is not encrypted, but it was signed by the CA. Encrypt hash code with the CA's private key.
Okay, yeah.
So that you can check it. So that's literally what you're doing in this problem. That additional component. All right. Okay, great. So yeah, so I think this is one really, how to do it. It's actually easy, but you just have to think about the whole steps. You will do this problem with your partner, and then, as I said, next week, not this week, we will. Actually, not next week because we have in 2 weeks then, because we have the exam. We will do this lab, which I think is a nice lab. And it shows you how you're going to become a certificate authority. You're going to have the key. We're going to create a client server architecture, and then you guys will do the whole process. Okay. All right. So now let's go ahead and I said we were going to do some commands, just kind of look at the keys a little bit more. So let's go back to the virtual machine. But you have 2 problems. You have 1 problem definitely for those of you that have finished your demo. You can do that problem on Thursday. And then on Thursday also, or today, talk about problem 1. All right. I'm going to be clear here. I'm going to step hell. All right. So we're using the OpenSSL library to generate certificates. These certificates are sometimes called the X509 certificates. So that's kind of the format. All right, so I created, let's see. So let's look at a new command here. This one will actually create a key and a certificate of the key, a self-signed certificate in this case. So let's take a look. All right, so I actually want to create a new folder for this because it's going to be a lot of files. So I'm just going to do mkdir, and I'm going to say certs. Okay. Now, it's going to be certs. All right, so let's look at this command. So openssl, and then we'll discuss it. Acquire -new -new key RSA 1024 days 365 nodes X509 key out will be let's call this public, should be public public.pem -out public cert. Cert, like that. Okay, so the output should be these two files. All right, and then it starts this whole process. Okay, and this will be actually the lab that you guys will be doing on next, in 2 weeks. Right, we're trying to create certificates. So the following command used to generate an X509 certificate for your keys. Okay. Again, I will. You don't have to do all of this for the last problem if you don't want to. Okay. Just keep it simple for problem 3, but this is more formal how you create the certificates. This outputs two files, which are public.pem and public.cert. The former containing key for 1024-bit. Oh, that generated the private key actually. So I was generating the private. Notice it says private key here. So we'll have to change the name. All right. The former containing a new private key for 1024-bit RSA, and the latter contains an X509 certificate that contains the public key. Okay, so that's what it is. All right, so we do have the public key, but it's in a certificate form, and then we have the private key, which of course you should keep private. Okay, so I'll need to rename those. Actually, I can just kill it because I didn't finish. So let's change this to private, right? There we go. All right, so hopefully that'll do it. So, and the latter is an X509 certificate that contains the public key and a self-signed version of the same. Okay, so it's actually creating this certificate thing with information. And then to verify that the certificate file contains everything that we need, we can check verify. So now let's go ahead and follow these instructions here. So we have to, because this is a more like another wrapper around the key with more information, we have to put in some things. So country name, 2-letter code, so I guess US. State or province name, so Indiana. City, some of these, by the way, I think we can leave blank, but I guess we can. It's important that you do this carefully also, because obviously when you reuse it, if you change a parameter, it could affect things. Okay. So Hammond, organization name, organizational units, CIT, common name. I'm just gonna leave this PNW. Email address, I don't think we need that. All right, and there we go. So it finished. You can see there's nothing there. Clear ls-l, and we have things that we need. So let's take a look at public cert. Right, there it is. It's got still a specific format. We can look at private. Does say it's a private key, right? And there you go. So now let's run the following command: openssl verify, and then it would be public cert. Okay. Self-signed certificate, verification failed, it says, but it does tell us that it's a signed certificate. This command prints out a message saying it's a self-signed certificate. That's about it. Now, if we want to see the text, and this is what I was getting at, if you want to see the text form in the terminal window of this certificate, we can try the following. So now I'm going to do openssl x509 -in public, right? Public dot cert dash text and dash no out. And there it is. You guys see that? So this is that same certificate, but in a human readable way. So let's take a look at what's inside. Certificate version 3, serial number, signature algorithm. Notice it says SHA-256 with RSA encryption. The issuer, the United States, Indiana, Hammond, PNW, CIT. So you can see it's got the information. Notice it's got this validity, right? So basically, you can create a certificate and you say how long that certificate is valid, and and if that way you can control certificates. So in fact, when you create these things, they don't last that long, right? So it makes sense, because if it takes a year to break one of these things, then just issue a new one every day or every month, whatever, whatever's convenient to you. And then it doesn't matter if somebody's trying to break it, next day there will be a new one. So then they'd have to start again and so on. Does that make sense, guys? All right. So yeah, so this is just the document itself, the X509 contains the key, but it basically provides more information about it. All right, so then it says here, subject public key info, public key algorithm is RSA encryption. This is an RSA public key, 1024-bit. Notice it does say public key, right? Key information. Do you see this? What is that? So you got the modulus, which is the N part, and then the E exponent, and it is 65537. So if I was writing this the way that we've been writing it as tuples, right? I would have 65537, comma, and then this big thing, which is in hexadecimal, basically. On the practical exam, or the scavenger hunt, you have to break RSA, correct? What if I gave you a certificate like this? Then you'd have to run public cert, this command, right? And then what would you look for to break RSA? The modulus, correct? And then you'd have to grab that and break it with factor DB, for instance. But what's the problem? It's encoded, so you'd have to encode it to something else, like a number. Do you see that, guys? All right. I'm not saying I'm going to do that necessarily, but I'm just stating that somebody that's trying to break your key would look at these certificates and look at that parameter, and that's the parameter that they would want to break. Correct? And this is easy to do, like, some Python code. I'm pretty sure it may already be on my GitHub. I may have some Python code that grabs that and converts it to some other formats. Okay? All right. So, but we're just looking through this. And then because it's a self-signed certificate, it does have the signature in there. And it says a SHA-256 with RSA. So that's a signature algorithm because it's a signed certificate. But sorry, it's a certificate, but it's a self-signed certificate. So it kind of generated something. Okay. Any questions, guys? So this is just us viewing these things. Okay. So with that previous command, we were just trying to print out the information in the certificate. Let's keep going. Okay, so we're going to try, let's see. So now let's do another example. We're going to generate a public key given a private key. So let's do that. Okay, so I don't want these to get confused. So I'm going to say my in this case, okay? I'm going to say open SSL gen RSA dash out. And I'm going to say my private key dot pem. And this is 1024. Okay, so I hit enter. It says generating RSA private key, 1024 bits, 2 primes, ls-l. There it is, right? You can see the size is kind of big. Okay, about the size for a 1024-bit modulus generated key. All right, now we're going to generate the public key given that private key. So we can do openssl RSA dash in my private key dot pem dash pub out, right? And then I'm just going to redirect, it's a Linux command, to my public key dot pem. All right, writing RSA key. So let's do ls-l. So I have my private key and my public key, and we can see that this one is smaller than the other one. I can take a look at them. My private, okay, there it is, private key. My public. Okay, so you know how to generate. Right, great. So the first command generates a private key and the second outputs the corresponding public key. If you want to extract the number of parameters from a PEM file containing a private key, we can do something like the following. I'm going to do openssl RSA dash text redirection my private key dot pem. And there it is. So that was the private key. And now we can, the thing that has been a mystery all semester, now we can kind of view it. So in this example, I took the my private key, right? And I'm just kind of printing it out, the parameters. I know it's an RSA private key. It's 1024-bit, 2 primes. Here's the modulus n, the public exponent, the private exponent. What's the private exponent? I'm gonna pick someone. What's the private exponent in the formulas? What letter? D, right? D. Yeah, very good. D. And then notice, if you remember, I had said that it keeps the prime numbers only in the private key, right? You should know that the prime number should not be in the public key, right? Because the whole point is that from n you get the prime numbers. So if the prime numbers were in the public key, you can break RSA. Why are they in the private key though? First of all, it doesn't matter because the private key is private, so no one's gonna, it's not a problem. Don't make it available. Also because you actually don't want to use, you can use n, but there's a more efficient algorithm that uses the prime numbers instead. Do you see what I'm saying? So when you're doing RSA, you could do like what we did with using n, but that's slower, less efficient. A more efficient approach is just to use the prime numbers themselves, and that's not a problem from the private key point of view. Okay, so that's the only reason why it's there. It's once again, it's yet another example of performance and why you're always trying to make the algorithms faster as everything is encrypted, right? So everything is slowing down the network every time you're encrypting and decrypting things. So it's a purely efficiency kind of a thing. Does this make sense, guys? So once again, I have given you the command, and I'm stating to you that you will have to break a public key on your scavenger hunt, right? If I gave you a public key, right, then you may need to look at it and extract something like this. And then if this is not in the right format, then it would need to be converted into the appropriate format in order for you to start breaking RSA. Got it? So that's kind of the idea. So obviously people would look at this and try to break RSA. Any questions about that? Seems like it's clear. So in this example, we wanted to extract the parameters from a PEM file, and look at them. And I did it for the private key, correct? Because I wanted to show you that the primes are there, right? And now I'm going to repeat the exercise basically, for the public key. ls-l. So I want to take a look at my public key. So once again, I'll repeat. So if I do cat my public, great, I can see that, but unfortunately, I can't make sense of it, right? I'm trying to break RSA. I'm going to look at this file, but I need to convert it to a readable thing. So I'm going to try openssl RSA dash text dash pub in my public key dot pem. So if this works, boom, we get that. Notice this one looks a little bit different. Why does it look different? Because they have different information. The public key, so let's take a look at the readable information. It says public key 1024-bit. This modulus is here. Now, you may be worried, like, what if I use this? Well, I probably can possibly, if I use 1024, you won't be able to factorize it, right? Think about that one. So, and then it doesn't let me use something very tiny either. So there's a disconnect. So I can't, and I'd have to have like a real powerful technique to break something this big. But anyway, this is the modulus. So this should be your n in hexadecimal format that you would factorize. Here's your e exponent. And then after that, it just gives you what we've seen. Good. Yeah. But that's how you can view the data and kind of make sense of it. All right. So both of the above commands will show the parameters. Now we can also, if we want to look at the modulus, we want it to be displayed as a more hex string, more readable. We can try the following. So we're going to do openssl RSA dash text dash pub in dash modulus, and then we can do this, my public I'm sorry, my public underscore key dot m. All right, and there you have it. So you have this one. This might be easier for conversion, right, and so on. You get the idea, right? So we're just playing with ways of viewing this information, and and so this brings up an interesting thing. I have pretty sure on my GitHub I had some functions for that. Let's take a look at GitHub. And where would that be? So could be under RSA. Yeah, I think. Oh yeah, convert hex to decimal. There it is. Yeah, so here I have a little example using Ruby. It does say hex modulus, right? And I think we have a hex modulus actually. So hex modulus, open RSA, pub in, modulus, grep modulus, blah, blah, blah. So how about we try this? What do you guys think? All right, so let's go ahead. We will need, I think, if you guys do this, you'll need Ruby on Rails, I think.
Nothing.
You don't like Ruby?
JavaScript's better.
Yeah. Yeah, I don't have an opinion. You can use another language if you'd like, but here let's try it. So now I'm just going to try the same exact thing, but wrapped around. Let's go back. Let's hopefully that copy. Let's go over here. Paste. Perfect. There we go. All right. So what are we doing here? So let me just take a look at yeah. All right. So I'm creating a variable hex modulus, which the name should imply that it's the modulus in hex format. I'm running openssl RSA dash pub in my public key pem. It's literally the same key I'm using, dash modulus, right? So this should be this one, right? openssl RSA. Okay, this one does say dash text pub in, but then I have a grep modulus. So if you took 372 with me, you should know what that is, right? So grep modulus, we're grepping that, which is basically just means we're grabbing this one here. And then just a cut, right, and get the fields, okay? So, all right, so hopefully that'll work. Okay. Hex modulus then. So now I should have this in theory, right, in that variable. Do you guys see that? And so now all we're going to do is convert that to, as the script implies. So it says convert hex to decimal. So I probably already have Ruby installed. So Ruby. Paste. Okay. And then it says this one. I think it was ELF. Yep. And there it is. Do you guys understand the idea? So now maybe you can factorize that. What's the problem though? It's too big, right? So that's the problem. So factor DB may not work for that one. I don't know, honestly. But as a nice exercise, right? I could give you a public key in this format. I could maybe just change this modulus to something smaller that I know you can factorize. So you would need to perform these commands to arrive at the decimal and then factorize that decimal. Does this make sense, guys? Do you have any questions? I'm talking about this for the scavenger hunt. Yeah, sir.
Regarding Ruby, we're having some trouble running it.
Yeah, it's the install thing. So this is my VM, and I probably did this last year. So if you try these two commands, does it work? Oh, really? So you'd have to run sudo apt update and then sudo apt install Ruby. See if you can try those two and then see if it runs. Has anyone tried it yet? Did it work? Okay, so we're fine. Thank you, by the way. So again, I'll repeat, in the scavenger hunt, I could give you a public key like that, right? And then you have to kind of run the commands that I just did, such as this one, the hex modulus one, and then run this Ruby one, and then you would end up with what you know how to process. The modulus in decimal form, then you can feed that into factor DB. The only problem with this one is it's too big, so factor DB may not be able to factorize it. But on the practical, I could just go in there and put in a smaller one. You see that I know you will be able to factorize. So I may do this, okay? Any questions? All right, great. So if you want to get those scripts, it sounds like, did anyone else try it and got it to work? Did it work for you?
Yeah.
Thank you. All right, perfect. So you can, of course, get this from the GitHub, convert hex to decimal. And as I said, I'll be working this week on creating the scavenger hunt. So I may add this in. I was playing with this recently. All right, yeah, so that's kind of what the goal was today, to just wrap up digital signatures, introduce certificate authorities. The certificate authority main lab will be in 2 weeks. So yeah, so that's kind of the idea. And then I wanted to give you these commands to be able to read the certificates and the keys in a little bit more detail. So let me just see if I have it. I'm almost done with my notes here. So let me just see if I have something else. Okay, and then the final one, I guess, if you want to look at the certificate, which we created one, right, in a text readable format, we can probably also do that. So I'm going to go back to my terminal, ls-l. So I do have a cert there, .cert public, which is a self-signed certificate. So I'm going to try openssl x509, right? So that's like the format or something, dash text. And then I'm going to redirect in there public dot cert. And there you go. So this one, just gives you the information, maybe in a more readable format. Okay. But I could do the same. I could put the information in the certificate. So then you would just grep on modulus and then basically extract the information. All right. So I think that's basically it for today. I'll check my notes, but I think I've covered everything. If I missed anything, I will cover it, in the next time.
Can you go back to the?
Yeah, please. Yeah. To which one?
With the script. Your GitHub.
Oh yeah. Yeah. You have to go to, it was under RSA. So go to the cryptography one, and then under RSA, it should be the script called convert hex to decimal.
Okay.
All right, guys. We can stop here for today. Yeah, we can stop here for today. I'll stay for a few minutes if you have any questions. Please remember, on Thursday, you need to demo, right? If you haven't done so already, it's your last chance. You do have a new lab that I posted, so you can work, for those of you that have finished, you can work on that on Thursday, or start preparing for the scavenger hunt, which I think will be a week from Thursday, right? What's as I said, I'm going to take a file, a quote from a movie, and I'm going to encrypt it in various ways. And you have to break it. And at the end of, you have to do it in class, in the lab. And before you leave, you have to give me a sheet of paper and you found it, right? And submit a report basically of how you did it. Got it? All right. And then also Tuesday is your written exam. All right. Have fun. Fun weekend, right? But I'll see you guys on Thursday. All right. So I'll end the session.